Chapter 3, the normal distribution. So the normal distribution is a specific shape distribution. It's the bell-shaped distribution that we saw at the end of Chapter 2. And we're going to learn in this activity about how we describe it, how we interpret the standard deviation, and a rule for finding the proportion of observations that lie within 1, 2, or 3 standard deviations. So make sure you read through the why and our learning objectives for this activity and the vocabulary. I'll be referencing this vocabulary in the discussion. So we want to think in example 1 about areas under density curves. So here is a histogram of grade equivalent vocabulary scores. These are 7th grade students who took a standardized test in Gary, Indiana. And the smooth curve is drawn over the histogram, and we see the smooth curve is the theoretical model, and then our actual data are these bars. The center is right around 7, which is what we expect because these are 7th grade students, so we expect their vocabulary scores for most students should be, or for the average at least, should be 7 or close to 7. So when we describe the shape, the range, and the center of the graph, we say the shape is symmetric, or roughly symmetric. It's got one peak. We say that's unimodal. Sometimes we'll see graphs with 2 peaks. We would call those bimodal. And the range is from 2 to 12. Well, the range is 12 minus 2. We would say the spread is from 2 to 12, and the range is 12 minus 2, which is 10 grades. I started to say points on the test, but we can think about them as grades. And then the center is a 7th grade test score. So 100% of these 7th grade students in Indiana are included in the histogram. So we know there are 947 students total. 287 of these students had vocabulary scores of 6.0 or lower. So what percent of students had vocabulary scores of 6 or lower? So we can, as a probability statement, say the probability that x is less than or equal to 6. We shaded those bars yellow here, so all the bars less than 6 are shaded. And so as a fraction, that's 287 out of 947, 0.303 as a decimal, or if you want to think about it as a percent, you could say 30.3%. So then if we want to think about, well, what percent had scores higher than 6, we can use the complement. So we can say, what's the probability that the score was greater than 6? So we could say 1 minus 0.303 and get 0.697, or we could say 947, subtract the 287 students, that's 660 divided by 947 total, and we get that same result. So this is the complement when we're finding the distance from the whole. And so that is 69.7% as a percent. Now we're told in Part D that 635 students had vocabulary scores of 8 or lower. So we want to know what percent of students had vocabulary scores higher than 8. So first we figure out, well, what's the probability that they were less than 8? That's 635 out of 947, or 0.671. And then I'm going to use the complement because I know these have to total 1 because everyone is included in this distribution. So to find the probability that the score is higher than 8, I can say 1 minus 0.671, which gives us 0.329 or 32.9%. So in this case, I'm using the complement, the fact that the total is 1. Example 2 is giving us now a skew density curve. We still do our calculations in the same way. So this is mileage along the x-axis, so I put a big X up here. And we see they're separated into bins. And then we've got the smooth curve with the right tail drawn over our histogram. So we want to describe the shape, center, and range of this histogram. So the shape is a right tail or a right skew. The center is right around 17 to 21. And we've got a couple ways of figuring that out. We know that there are 100 cars, so you can check 18 plus 39 is 57. So we know that middle 50th and 51st car, the middle 2 cars must be in this bar from 17 to 21 in that bin. So we say the center is 17 to 21 miles per gallon because the median is in this bar. We don't have individual scores, so we can't easily calculate an average. And then the range is going to be 41 minus 12, or 29 miles per gallon, because we say the spread from 12 to 41 And then we subtract the spread to find the range. So the EPA is concerned about cars with mileages 21 miles per gallon or less. So using the histogram bars to count, we can figure out what percent of cars in this random selection have mileages 21 miles per gallon or less. So counting up the column values, we can add up 39 and 18 to get 57 out of 100, or 0.57, or 57% of cars have mileage 21 miles per gallon or less. So the EPA goal is for a majority of cars to have mileage 27 miles per gallon or higher. So we want to know what percent of cars in this random selection meet this goal. So we come back to our histogram frequency table here, and we add up the values for 27 and higher mileage per gallon. So 9 plus 5 plus 2 gives us 16 out of 100, or 0.16, or 16%. So this is not a majority of cars meeting our goal. And then lastly, how do the histogram bars compare to the area under the smooth density curve? So I say here the fit is just okay. For better fit, we would want smaller bins to make narrower bars. Here in example 3 is what we call a uniform density curve. So you can see here that one face came up a bit more than, I should say, 170 times. And that is, which face came up the most here? I think it was the face 2, right? So this is if you're rolling a die 1,000 times, we'd expect them each to come up evenly, which would be roughly 170 times. And so just due to chance, we're a little bit off of the 170, which corresponds with 17%. 170 divided by 1,000, that's where the 17% is coming from. So this is called a uniform distribution because it's pretty flat. There's no difference in the bar heights. So we want to check, does this uniform graph satisfy the requirements for a density curve? So you check to see, does it only have positive y values, and does it contain 100% of the population data? So when we do our check, all y values are positive, and the total, if you add up those percentages, is 100%. So this is considered a density curve. Now, if you want to know what proportion of the die rolls are between 3 and 5, including 3 and 5, you can add up the heights of those bars. So if we come here and add, I made them decimals, 0.17, 0.162, 0.159, we get 0.491, which is close to half as a proportion. That's what we expect because these are 3 out of the 6 possible faces. Now, Chandra is in a heated board game with friends, and she needs to roll a 5 or higher to win. What proportion of the die rolls should she expect to be 5 or higher? So we know 5 is going to come up 1 out of 6 times. 6 is going to come up 1 out of 6 times. So we can add up these probabilities because they are mutually exclusive, right? She's not going to roll both a 5 and a 6 at the same time. So if we add up 1 6 and 1 6, we get 2 6 or 1/3 or 0.3 with a bar. So notice here in this notation I'm saying the probability x is greater than or equal to 5. When we were figuring out the probability of being between 3 and 5, we used the inequality with x in the middle in this way. So this is saying 3 is less than x, which is less than 5, which is saying x is between 3 and 5. So we've looked in the previous chapter at the relationship between mean and median. So this is a little bit review. So we're using m here for the median and Greek mu for the population mean. And so we see if the mean is less than the median, we expect a left skew. And if the mean is higher than the median, we expect a right skew. And then what shape is a curve where the mean and the median are the same value? So if it's a normal distribution of bell shape, we're going to get this symmetric curve that looks like a bell with one peak. A uniform distribution would also be considered a symmetric curve, right? It's less interesting, but it still is balanced area on both sides. In a recent local election, the mean voting age was 56 years old and the median voting age was 49 years old. So what shape is the corresponding density curve? So in this case, our mean is larger, 56 is larger than our median, so we expect it to be skew right. And I gave a little sketch here. We can label, here's our median, age 49, here's our mean, age 56. And we're using mu for the population mean here. Remember, x bar is our notation for our sample mean. So this bell curve is known as the normal distribution or the Gaussian curve. You can take a minute and pause and read through this page about Carl Friedrich Gauss, who they named the curve after and call it the Gaussian curve. Abraham de Moivre was the first mathematician to discover this normal distribution in the 1700s. He was working as a consultant to gamblers and studying the distribution of heads when flipping a coin. Here's the formula for this normal distribution curve. It is quite messy. So notice this formula has a little bit of everything in it. We've got sigma for the standard deviation. We've got a square root. We've got 2 pi in here. We've got e, that's the base for a continuous curve. Up in the exponent, we've got x minus a mean that's squared. It's divided by 2 times the standard deviation squared. So this is quite a messy formula. I will not be asking you to work with this formula this semester. All area calculations are going to be done in StatCrunch. A student in calculus might have to manipulate this messy formula, but typically it's something that we outsource to computers to calculate or estimate the area for us. So in function notation, we call this f of x. So function of x is how we read function notation. The input is x and the output is f. Sometimes you'll see it as p of x to indicate that the output p could be interpreted as a probability of the input x, or you'll see it as phi of x, the Greek letter phi. So if you go look in a statistics text, you'll see the formula written all these different ways. Again, this is not a formula you should be doing any work with. If you find yourself plugging in the standard deviation and the mean, pause and shift over to technology to do your calculations for you. So here's 2 graphs. So we want to think about how are they similar and how are they different. So these are both symmetric, normal shape distributions. They both have the same standard deviation. They're both stretched the same amount on the horizontal axis. The difference is that this graph here is centered at 0, whereas this graph is centered at 5. So the mean determines the center of the normal distribution. For a symmetric distribution, we expect to see the peak at the mean, the average values, with an even amount of data higher and lower than the mean. So in the distributions above, these are both considered symmetric because we've got balanced distributions with no skews. Let's look at standard deviation. So here is a pinkish graph and a yellow graph. So these are both centered at 50, but they have different standard deviations. So this shorter yellow graph has a greater standard deviation because its spread from 20 to 80 is wider than the lower spread. And so we say this shorter curve or the yellow curve has a greater standard deviation because it has a wider spread. So now we want to calculate the range for each graph. So for the short curve, the yellow curve, we could say 80 subtract 20 is our range. It has a range of 60. And for the tall curve, we could say 70, or 65 I said, subtract 35, which gives us a range of 30. So we know the area under the normal distribution graph must total 1 or 100%. So how does this graph with the smaller standard deviation compensate? So this pink graph has a smaller range, but notice it's taller. So if you imagine squishing the top of the pink curve, you could stop at a point where it should match the yellow curve if you could squish the top and get it to spread out. So they should have the same area, 1 or 100%. So we have a rule here, and notice this pink is just the ink coming through from the other side of the paper. There's nothing special about the pink normal distribution curve here. So the 68, 95, 99.7% rule approximates the area within 1, 2, and 3 standard deviations. So we say approximately 68% of the observations fall within 1 standard deviation of the mean, meaning we go up 1 standard deviation or down 1 standard deviation. In this graph here, the mean is 100, and each standard deviation value is 10. So we can say we go up to 110 and down to 90 to capture 68% of the data. If we come out 2 standard deviations, that captures 96% of the data. So these numbers come from calculus, counting up the area under this curve. It's not any calculations you're going to do by hand. We're going to outsource these to StatCrunch. And then if we come out 3 standard deviations, down to 70 and up to 130, that captures 99.7% of the observations. So no matter what your values are here and your values for the standard deviation, you're going to have these same percentages correspond as long as you're working with this normal distribution shape. Here's a diagram of drawing it out to break it down. So the mean minus 1 standard deviation up to the mean, that's half of the 68% of the 34%. And then knowing that everything adds up to 100%, you can see how these values work out. There's always a little bit outside, so we don't ever want to say we've captured 100% of the data, because imagine if we were thinking about heights, you could have some taller person come along. So you don't ever want to say I've got 100% of people within this range. So we see here, even if we're out plus 3 standard deviations, we still have 0.15% that could be beyond that. So there's always a little room for somebody higher or lower. So let's fill in a normal distribution for the test we looked at from students in Gary, Indiana. So here the mean is 6.84 on that test and the standard deviation is 1.55. So using that fact, we put 6.84 here in the center for our mean, and then we come up adding 1.55, add another 1.55, add another 1.55, and then we subtract 1.55 to go down to fill in the distribution curve. So if we want to know what's the range of scores for 68% of the data, we know 68% of the data is between subtracting 1 standard deviation and adding 1 standard deviation. So here I'm using sigma for shorthand instead of writing out standard deviation. So if we look back up here, that is scores from 5.29 to 8.39. And you can do it mathematically. You could say 6.84 minus 1 standard deviation is that lower bound of 5.29, and 6.84 plus 1.55 is the upper bound of 8.39. So now what's the range for 95% of the data? So we can come back up to our normal distribution curve here and come down 2 standard deviations and up 2 standard deviations to see the values. You can also mathematize it by saying 6.84 minus 2 times the standard deviation. Remember, order of operations, you're going to multiply first before you subtract. And so we get that 3.74 lower bound, which is what we see in our graph. And similarly, when we're adding the mean plus 2 times the standard deviation, we get 9.94, the same upper bound we saw in the graph. Question D wants to know what scores the cutoff where 2.5% of students score higher. So I put our percentages on here. So we see after a score of 9.94, we've got in this range 2.35% of students, and then there's 0.15% of students that score higher than 3 standard deviations. Those are the point at which we'd say these are unusual students or outliers. And so we can see if we add those percentages up, we've got 2.5% of students higher than a score of 9.94. So we're able to say for scores of 9.94 and higher, the area is 2.5%. So 2.5% of students score higher than 9.94. Similarly, if we want to know what percent of scores are higher than 5.29, we can come back to our chart over here and add up the areas more than 5.29. So I broke it down. We've got 34%, 34%, 13.5%, 2.35%, and 0.15%. And we can tally those up and see 84% of students score higher than 5.29. And then if we want to know what percent are lower, we can use the complement. So we know we've got 100% minus 84% is 16% lower than that. Now if we want to know what percentage of scores are higher than 8.39%, again we can come back to our distribution and add the areas. So we can add up all these percentages higher than 8.39, 13.5% plus 2.35% plus 0.15%. And then we come back down and see that tallies up to 16%. So if we want to know what percent are lower than 8.39, we can use the complement. So we can say 100% minus 16% is 84% here. So let's look at example 8, applying the 68.99.7% rule. So the shorthand way of writing normal distribution is n, meaning it's a normal curve, and it's a function of both the mean and the standard deviation. Remember, we have that complicated formula that depends on the mean and the standard deviation. So n tells us it's a normal distribution, and then the variables are the mean and the standard deviation. So summer monsoons in India are approximately normal with a mean of 852 millimeters and a standard deviation of 82 millimeters. So we can use these values to fill in the normal distribution curve. So you see, here's our center at 852, and then adding and subtracting our standard deviation of 82, we're able to fill in these values. I filled in the percentages also. You can double check to make sure all of our percentages add up to 100%. Notice above the mean is 50% of the data, so the mean is also the median, right? And similarly, less than the mean is 50% of the data. So we want to know between what values do the monsoon rains fall in 95% of all years. So that's going to be down 2 standard deviations and up 2 standard deviations. So those are rainfalls of 688 millimeters to 1,016 millimeters. And if you want to try to convert these to inches, you can use the fact that 25.4 millimeters is 1 inch, and grab your calculator and divide by 25.4 if you want to think about how does that compare to our Bay Area rainfall numbers. So question C asks, how high are the monsoon rains in the top 0.15% of years? So the top 0.15% of years corresponds to +3 standard deviations and higher values. So if we come look at our distribution here, here's the center. We count up 1, 2, 3 standard deviations. That is 1,098 millimeters and higher. We always want to make sure we're saying and higher, because there could be some year with an even higher rainfall that comes along. So we never want to say we've got an absolute upper limit for rainfall or an absolute lower limit. So how small are the monsoon rains in the driest 2.5% of years? So this corresponds to -2 standard deviations and lower. So if we look up here, we see here's our center. We come down 2 standard deviations. That is 688 millimeters and lower. And then in 2015, the actual rainfall was 760.6 millimeters. So we want to know how many standard deviations that is. So if you come back to the chart here, you'll see I try to draw in where 760.6 millimeters would be. I just put it a little less than 770 millimeters. It's not a precise drawing. So we see it's going to be a little more than 1 standard deviation below the mean. So I said minus 1.3 sigma from the mean, or about 1.3 standard deviations below the mean. And so I said about 12% of monsoon rains would be less than 760.6. So I did that kind of adding up. I know all of this would total 16% here, but it's not all the way up to 770. So I said, okay, this eyeballish looks like maybe 12% less than that. So we can be more precise in this estimate. So we can work backwards to try to find exactly how many standard deviations away we are. So here's our formula. We were saying 852 plus however many standard deviations we were, times our standard deviation of 82, and we expect to end up at 760.6. So using algebra, if we want to solve for z, which is representing the number of standard deviations, we can subtract 852. So we subtract that from both sides, and we get z times 82 is 760.6 minus 852. And then to get z by itself, we need to divide by 82. So order of operations says in a fraction like this, we do the numerator calculation first and then the denominator calculation before we divide. So we get negative 91.4 divided by 82, or negative 1.15 standard deviations away from the mean. So this is pretty close to my estimate of 1.3 standard deviations. This is telling us a precise value. So how do we figure out, well, what area is that? So we're going to use technology to recreate this picture since it's not a nice even 1, 2, or 3 standard deviations. So in StatCrunch, we go to Stat Calculators, Normal Calculator. And then we want to put in the mean and standard deviation that correspond. So if we look back at our distribution, we know the mean is 852 and the standard deviation is 82. So we fill those values in. And I got here in StatCrunch just by opening a blank StatCrunch. So you don't need to be in any particular file to access this. You can just go Stat Calculators, Normal Calculator, and you don't need to save your file at all. So our mean is 852 and our standard deviation is 82. So now we're trying to figure out the probability that is less than 760.6 millimeters. So we put that in our inequality and compute. And so here is the exact area calculated for us. So we see this is a match for our diagram here. So we can say 0.1325 proportion of rainfalls are less than 760.6 millimeters. If you wanted to translate it to a percent, you could say 13.25%. So the generic formula for that calculation we did is this. Z tells us the number of standard deviations. We take our particular value, in this case it was 760.6, subtract the mean, and then divide by the standard deviation. So in 2016, Northeast India experienced a heavier summer monsoon than the previous year for a total of 1,111.9 millimeters rainfall. This is the real value that I looked up. So we want to know how many standard deviations from the mean is this. So we would subtract, following our formula, our x value is 1,111.9 minus 852. That gives us 259.9. And then we divide by 82. This is a higher value, so we're getting a positive difference from the mean. So that is more than 3 standard deviations. So we'd say this is an unusual year. So I might ask, well, what proportion of monsoon rains are less than 1,111.9 millimeters? So I'm going to go back to StatCrunch, and I'm going to leave the same mean and standard deviation, but I'm going to change now my value to 1,111 point, was it 0.6? Let me look back. 0.9. And compute, and we get 0.9992. You can see this is so far out here that it's not even showing up on our graph here. Oh, and notice this graph by default, it counts by hundreds. If I want to see the tick marks, you just click 68, 95, 99.7 ticks, and it shows us the standard deviation counts. So you can see this is a match for what I filled in here. I rounded to 4 decimal places. That's a good rule of thumb. And then if we want to know, well, what percent are greater than 1,111.9 millimeters, you can use the complement. You can see, oh, 1 minus 0.9992 is 0.008, or you can go check just by clicking here and switching the direction of the inequality, and we see 0.00076 is going to round up to 0.0008. If ever you want to know between certain values, you can click here in the between and see how you could put different values. So say I wanted to know between 688 and 852. See how it shades this value. Oh, I put negative 688. I just meant to put 688. See how it shades this value, and it tells me right around 0.4772 probability of being in there. If you wanted to check 770 to 852, there's that 34% or 0.34 as a decimal. So before StatCrunch, students carried around tables with the normal distribution values in it. And so I put those in the next page. You can always use those. So here our z-score is 3.1695. So if we come look that up, the first page are negative z-scores, less than the mean. And the next page are positive z-scores, higher than the mean. So we are looking up 3.16. So the 3.1 is in this row. And then let's just verify it was 3.16. Yeah, 3.169, so we could say 3.17 standard deviations. Then the columns correspond with the hundredths place. So 3.17 is going to be in this column. So if we follow this column down to 3.1, we get 0.9992 right here as the probability of being less than 3.17 standard deviations, which is a exact match for what we got in StatCrunch. Typically, StatCrunch is going to be more accurate than the table, so you may sometimes have a more accurate number from StatCrunch and a slightly rounded value from the table. You can always use the table. On the midterm, I'll give you a copy of the table to use since we won't necessarily have technology. So you can have the table out. When you're doing your homework, it's probably just as easy to use StatCrunch as the table.